When engineers first tried to feed high-resolution images into early artificial intelligence systems, the networks collapsed under their own data weight. Traditional fully connected neural networks operate on a simple mathematical rule. Every single input pixel must connect to every single neuron in the very first processing layer. To process an image this way, the system has to flatten it, taking a two-dimensional grid of pixels and stretching it into a single, massive one-dimensional row. This process destroys all spatial relationships between neighboring pixels, and for a modern high-definition image, it generates billions of individual connections, creating an impossible computational overhead. Scaling image recognition required a completely different architecture. Engineers needed a system that respected the local physical relationships between pixels. The solution was the Convolutional Neural Network, or CNN. This framework was built specifically around the concept of spatial locality, meaning it processes data in small, regional blocks rather than reading the entire image simultaneously. This diagram shows how the core mechanism operates. Instead of reading the whole grid at once, it uses a shared, learnable filter, often called a kernel, that systematically slides across the input grid. We are going to trace the exact mathematical pipeline of a standard CNN. Then, we will examine how researchers rewired this basic topology to solve the specific mathematical bottlenecks that appeared when networks were scaled up. Tracing this development from basic filters to complex residual networks reveals the structural logic that allows these systems to scale. The mathematical pipeline begins with a standard set of parameters. Let's start with a 32 by 32 by 3 RGB input volume. RGB stands for red, green, and blue, meaning the image is composed of 3 distinct color channels stacked together. This diagram illustrates the convolution operation. As the learnable filter slides over the pixels, it calculates a dot product. A dot product is a mathematical operation that multiplies corresponding values between the filter and the image, then sums them up to produce a single output number. This calculation extrudes a new, deeper 3D block known as a feature map. Applying one filter creates a single layer of this feature map. By applying 12 distinct filters over the same input grid, the network generates this exact 32 by 32 by 12 volume. Each filter is learning something different. Early filters in the sequence usually calculate simple visual data like sharp edges, while deeper filters combine those local edges to learn complex textures and geometric shapes. Next, the network introduces nonlinearity by applying the ReLU activation function. ReLU stands for Rectified Linear Unit, which is a mathematical function that simply maps all negative values in the tensor to 0, allowing the network to model highly complex patterns. The combination of the convolution and activation stages successfully translates raw pixel data into mathematical feature maps, doing so without exploding the overall parameter count. As the network extracts these features, it generates massive amounts of data. This diagram shows how the network must aggressively reduce the spatial dimensions of those feature maps to maintain computational efficiency. This specific mechanical operation is called 2x2 max pooling with a stride of 2. A stride determines the exact number of pixels the filter shifts per step. By stepping 2 pixels at a time and only keeping the maximum numerical value in each 2x2 window, the spatial dimensions halve, but the depth of 12 remains constant. Max pooling serves 2 purposes: drastic dimensionality reduction and the creation of translation invariance. Translation invariance is a property where the network correctly recognizes a feature, even if it shifts slightly from its original location in the image. After several rounds of convolution and pooling, the final 16 by 16 by 12 volume is unrolled into a single, continuous, one-dimensional vector containing exactly 3072 values. This flattened vector is then fed into a traditional, dense, fully connected layer, allowing the network to evaluate all the consolidated features at once. The final step applies the softmax function to this dense layer. Softmax is a mathematical function that converts raw numerical outputs into a set of precise class probabilities that always add up to 100%. The baseline CNN operates as a systematic dimensionality reduction engine, distilling massive spatial grids down to final semantic predictions. To process more difficult visual tasks, engineers tried adding more layers. But this visual illustrates the fundamental barrier to making neural networks smarter: the rapid degradation of the learning signal. To capture highly complex real-world features, systems required a much deeper architecture, forcing engineers to stack multiple convolution and pooling blocks in long sequences. This linear approach hit a severe structural bottleneck in early deep architectures like AlexNet, an issue known as the vanishing gradient problem. Networks learn through backpropagation. Backpropagation is an algorithm that calculates error gradients at the end of the network and sends them backward through the layers to update weights. Because these gradients are multiplied by small fractions over long distances, the data signals literally fade away before they reach the early layers. Stacking layers in a straight line hit a mathematical ceiling, where increasing the depth of the network led to higher error rates. This flowchart illustrates GoogleNet's structural workaround to the depth bottleneck, deliberately moving away from a single linear path. This design is called the inception module. Instead of choosing one filter size, the architecture applies 1x1, 3x3, and 5x5 convolutions simultaneously, alongside a parallel pooling layer. Because of this parallel structure, the network captures visual patterns at multiple scales at the exact same time. At the end of the module, these 4 parallel paths are concatenated back together. Concatenation is the process of stacking multiple individual feature maps together along the depth dimension to form a single continuous output. The crucial element here is the 1x1 convolution, which acts as a depth compressor. By shrinking the feature maps before the larger convolutions run, it massively reduces the overall parameter count compared to early linear models. GoogleNet proved that the specific topological wiring of a network matters just as much as its raw depth. The definitive solution to the vanishing gradient arrived when researcher Kaiming He introduced the 152-layer residual network, or ResNet. This diagram displays the ResNet building block. Notice the primary processing path moving downward through 2 weight layers, but look specifically at the prominent skip connection arcing over them, which takes the input and adds it directly to the output. This physical bypass establishes the residual learning formula, f of x equals h of x minus x. By adding the input x back into the output, the network initializes close to the identity function. An identity function is a state where the output exactly matches the input, meaning the block only has to learn the minor mathematical adjustments, the residuals, instead of calculating the entire transformation from scratch. During backpropagation, the gradient signal flows unimpeded backward directly across this shortcut connection, safely bypassing the inner layers that degrade the signal. Skip connections create a gradient highway, allowing early layers to learn effectively even in ultra-deep networks. This diagram shows DenseNet, the maximalist evolution of the shortcut connection. In a dense block, Layer 1 connects to layers 2, 3, and 4, creating heavily interwoven pathways. DenseNet enforces a strict architectural rule: connect the output of every layer directly to the input of every subsequent layer through channel concatenation. To manage the resulting parameter explosion, DenseNet aggressively uses 1x1 convolutions to reduce the channel count down to a smaller size before applying the standard 3x3 convolutions. DenseNet maximizes feature reuse and ensures perfect gradient flow, representing the logical extreme of a densely wired architecture. CNN topologies evolved from basic feature extractors to massive computational graphs. A straight line, AlexNet, transforms into the parallel branches of GoogleNet. Those branches morph into the overlapping skip connections of ResNet. Finally, those arcs multiply into the fully interwoven, densely connected blocks of DenseNet. As vision tasks grew more complex, the primary engineering challenge shifted entirely away from the basic spatial mathematics of sliding filters and became a problem of managing gradient flow across these massive network graphs. These iterations, branching, skipping, and concatenating, eliminated the depth bottleneck entirely. These specific topological designs provide the mechanics for modern computer vision to achieve high accuracy in autonomous navigation and medical diagnosis.